Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the entropy change of reacting systems. So far, we have analyzed combustion process from the conservation of mass and the conservation of energy points of view. The thermodynamic analysis of a process is not complete, however, without the examination of the second law aspects. Of particular interest are the exergy and exergy destruction, both of which are related to entropy. The entropy balance relations developed in Project 3 are equally applicable to both reacting and non-reacting systems, provided that the entropies of individual constituents are evaluated properly using a common basis. The entropy balance for any system undergoing any process can be expressed as, using quantities per unit mole of fuel and taking the positive direction of heat transfer to be the system, the entropy balance relation can be expressed more explicitly for a closed or steady flow reacting system as, where Tk is temperature at the boundary, where Qk crosses it. For an adiabatic process, the entropy transfer term drops out and the entropy balance reduces to equation 1318. The total entropy generated during a process can be determined by applying the entropy balance to an extended system that includes the system itself and its immediate surroundings, where external irreversibilities might be occurring. When evaluating the entropy transfer between an extended system and the surroundings, the boundary temperature of the extended system is simply taken to be the environment temperature, as explained in Project 3. The determination of the entropy change associated with a chemical reaction system to be straightforward, except for one thing: the entropy relations for the reactants and the products involve the entropies of the components, not entropy changes, which was the case for non-reacting systems. Thus, we are faced with the problem of finding a common base for the entropy of all substances, as we did with entropy. The search for such a common base led to the establishment of the third law of thermodynamics in the early part of the last century. The third law was expressed as the entropy of a pure crystalline substance at absolute zero temperature is zero. Therefore, the third law of thermodynamics provides an absolute base for the entropy values for all substances. Entropy values relative to this base are called the absolute entropy. The absolute entropy values listed in appendices for various gases such as nitrogen, oxygen, carbon monoxide, carbon dioxide, hydrogen, water, OH, and O are the ideal gas absolute entropy values at the specified temperature and antipressure of 1 atm. The absolute entropy values for various fuels are listed in appendices together with the enthalpy of formation values and the standard reference state of 25 degrees centigrade and 1 atm. Equation 1318 is a general relation for the entropy change of a reacting system. It requires the determination of the entropy of each individual component of the reactants and the products, which in general is not very easy to do. The entropy calculations can be simplified somewhat if the gaseous components of the reactants and the products are approximated as ideal gases. However, entropy calculations are never as easy as enthalpy or internal energy calculations, since entropy is a function of both temperature and pressure, even for ideal gases. When evaluating the entropy of a component of an ideal gas mixture, we should use the temperature and the partial pressure of the component. Note that the temperature of a component is the same as the temperature of the mixture, and the partial pressure of a component is equal to the mixture pressure multiplied by the mole fraction of the component. Absolute entropy values and pressures other than P0 equals 1 atm for any temperature T can be obtained from the ideal gas entropy change relation written for an imaginary isothermal process between states T, P0, and Tp, as illustrated in the figure. If a gas mixture is at a relatively high pressure or low temperature, the deviation from the ideal gas behavior should be accounted for by incorporating more accurate equations of state or the generalized entropy charts. Once the total entropy change or the entropy generation is evaluated, the exergy destroyed EL associated with a chemical reaction can be determined from this relation. Okay, that's all for this task. Thank you very much, and see you next time.